just going to keep asking questions about
They
what
want
you're
to sign
saying.
why. The number I have doesn't look like this.
Sounds good. All right, thank you.
That's a problem.
Bye.
Basically, they're saying that.
Yes.
That's actually really neat. I'm just going to skip it. Like, there's this place right here, but that's page.
Positive view on
Oh.
Thanks for coming. So, I would invite class members maybe to line up and take photo because, as you've seen in previous years, it can be placed on the back cover. And every visitor is also fine to stop by and
Where do you want us to stand?
just near the screen.
Here, Dimitri, I can take it for you.
Oh, thank you.
Oh.
Okay, you're taller, so you go in the back.
Yeah, I'm going back.
Are we all supposed to hold one?
Short people in front, tall people in the back.
I'm not supposed to hold one, so
I am, sir.
I'll just stay right here.
Stay in front.
No, camera's not on.
Okay. Are you not going to get in the picture?
Huh? Okay, I can.
Oh, yeah,
I can, yeah. Thank you.
Ready?
It's a good idea.
Okay, I think I got some.
Okay, yeah, thank you.
Yeah. When did you get here?
Oh, Sudipto.
Oh, Sadito!
We will paste him. Draw a cartoon.
Yeah, let's just get them in a second.
Oh, you can sit here.
Are we gonna?
I won't hide, I promise.
You're eating clean.
Oh, the only ones I like. That's
How's it going?
Okay, welcome to the last meeting in the Introduction to Computational Chemistry course. And make yourself comfortable, take some snacks. If you dig inside coolers, there should be ice cream. Feel free to pass it over, which is needed at a hot day. So the course was running for, as a course should run, for half a year. And the goal of the course was to combine all necessary components for computational modeling of so when it started with the theories background, and then went through practical skills of building models and running correct software and correct hardware. So this whole activity is needed to compute some characteristics, some observables of real materials, compare them to experiment, and also, of course, includes a component of scientific communications, which is substantially practiced right now. So, also participants of the course written mini papers, which are here that you can enjoy, and the course, if you are coming here for the first time, the course was consisting of 4 components with the basic ideas of the modeling molecules, the electronic structure of theory, density function of theory as workhorse for modeling anything, and excited state. So the presentations today are 3 real additions to the course. Every participant volunteered to do this bit of mini research as a replacement of an exam. So in some sense, it is a final exam for the course. So the presentations are expected to run only for 5 minutes. Otherwise, this large amount of talented young researchers will not finish in time. Right? But if you see on the schedule, it's assigned about 10 minutes because when it's time to walk front, put things, and last but not least, to answer questions. So the presentations are arranged on 4 chapters. So there will be presentations of mini research related to quantum confinement. Some will be related to charge transfer, some to chemical reactions, and also last but not least related to some novel advanced materials. In case you have never seen Microsoft Windows, if you have never seen Microsoft PowerPoint, here it is, and the presentations are arranged here by number in the queue and by first name. So identify yourself, click, and start presenting. So while the first speaker is coming up front and prepares to present, here is the advancer. If it doesn't work, there is that one can just click keyboard and mouse. And I will distribute forms that visitors and participants can fill, providing feedback on what you see. Okay, the first speaker is David Brocker, and he will tell us something about exotic form of perovskite. Floor is yours.
So I was examining Rudolson-Popper perovskites, and so the generic perovskite, you see a generic layer here. It has a ABX3 crystal structure. So what that is the A and the B are cation, and the X is anion. In my case, I'm looking at cesium lead chloride perovskites. So then what the Rudolson-Popper perovskite is it, in addition to these ABX3 layers, you have AX layers that offset them. And there's a second type of Rudolson-Popper perovskites. It's called hybrid Rudolson-Popper, that instead of an AX layer, it uses a layer of organic ligands to separate. So here you have the 2 models I was looking at. So on the left here, you have the hybrid Rudolson-Popper perovskite, and the organic ligands that I was using to separate it was a propyl 1,3-diammonium. And over here you have the Rudolson-Popper phase perovskite. And so the perovskites themselves, which are these structures, are cesium lead chloride, but the halide that was used to separate them is a iodine. And you'll notice that if you look at it, the ligands are, the perovskite layers are offset from each other between the top and the bottom. So here we have the density of states and absorption spectra for both of my models. So A and C are the hybrid Rudolson-Popper, where B and D are the Rudolson-Popper phase perovskite. And they have similar absorption spectra, although the hybrid does show a small peak around 450 nanometers. And here we have the HOMO and LUMO orbitals of my hybrid model. So the blue orbitals are the HOMO, where the red are the LUMO. And this figure off to the side of each is the one-dimensional projection of these. orbitals, and you'll notice that in the LUMO, the orbitals are localized on the lead atoms, where they're more spread out in the HOMO. And here is the same model for my Ruddleson Poplar perovskite. This one, there's localization on the halide atoms for the HOMO, where the LUMO, said that backwards. The LUMO has the localization on the halides, where on the HOMO it's localized on the halides and the cesiums. Not the cesiums, the leads. This is the molecular dynamics of the hybrid Ruddleson Poplar model. You'll notice that most of the activity appears to be localized to the organic ligands that separate the layers. So, in conclusion, we see that these two layers have similar absorption spectra, and but to really determine any usefulness as in photovoltaics or as a light-emitting material, we would need to determine their non-radiative relaxation rates. We should also need to examine what the effects of additional perovskite layers. Both of the models I was using had 3 perovskite layers before the intermediate layer that offset them. And we also need to use different halides for this process. It has been shown by other groups that halides affect the band gap of these materials.
That's it? Okay, let's thank the... Any questions to the speaker?
Yeah.
Can you go back to your density of states? So I noticed it looks like B is a larger gap.
B does have a larger gap. It was approximately a 2.8 EV gap for the Ruddleson Poplar phase, where the hybrid had approximately a 2.3 EV gap.
What do you think accounted for that change? So to see the gap go up makes me kind of wonder if it's losing kind of its...
So I know that in these materials, when you use the larger halides, the band gap decreases, but that doesn't make sense for this situation. So the iodine instead of chlorine, or bromine instead of chlorine, for instance, decreases the band gap. But that wouldn't make sense here, as I am not sure what would cause that.
Okay, more questions?
Yeah.
Can you go back to your models? You kind of never explained which are ABX3, man. You just showed us all these dots and the colors. You never. I didn't know what I was looking at. I was wondering if you could talk about that again.
So right here, trying to outline it. You have the perovskite cell. So here is a single layer of perovskites, and you have in the layer you have your perovskites. In this case, I was using lead. Would be this blue. Chlorine would be that orange. And in this model, they were using methyl ammonium instead of a simple halide. But this group right here would be the cesium. what this is, and I wasn't able to get bonds to show on this one without connecting it to the organic ligands. But if you look at it, this brown colored atom is the lead, the greens are the chlorines, and the pink colored is the cesium. And it makes that same shape that we see in that last one, or that last model.
Last chance for quick question.
Yeah.
It's kind of related to the first question from Mary. Can you, what's the origin? Can you go to your orbitals for the structure A and B?
Structure B?
Well, to compare orbit, because you show this is the same structure but HOMO-LUMO, right?
Yes, the blue is HOMO, the red is LUMO.
And this is for which structure these orbitals corresponds to your DOS?
That corresponds to
With
the
the smaller
DOS
one.
that was on the left.
With a larger band gap, right?
Yeah, the larger band gap.
Okay.
It corresponds to the B.
So the larger band gap having HOMO-LUMO orbitals, and again show everyone where the orbitals located. Okay, so they are on this intermediate, how to say, connecting inorganic molecules or atoms actually, right? Between the unit cells.
The layer, the iodine and cesium layer.
Now go to the case A for the DOS. Okay, and here's your HOMO-LUMO, and they do not really sit on this kind of.
No, they're only in the perovskite here.
So probably this is the reason, right? So that you have this organic contribution of organic molecules, right?
Yeah.
Because this is three-dimensional structure.
This is a two-dimensional.
Oh.
Yeah, this is a three-dimensional structure.
Three-dimensional, three-dimensional. Is it like we have top and bottom, or it's in a periodic?
Thin film has two-dimensional features, but it is represented.
But anyway, so here the surface is completely isolated by these ligands, right? And they do not contribute to your HOMO-LUMO gap, while the other ones have these orbitals of top and bottom completely occupied, and this probably caused this difference in the band gap, right?
So organic layer works as insulator, and inorganic does not.
Yeah. Okay.
Let's thank David once again. And the next presentation is by Kevin Gima. So from two-dimensional thin films, he will move us to one-dimensional nanowires. And from three-component perovskites, he will move us to two-component light telluride materials.
Alright. Hi guys, my name is Kevin Gima, and I investigated the question, are PBTE nanowires ideal thermoelectric materials for semiconductors? Alright, so first I'm going to basically give an introduction as to the basic concepts so you guys can understand my research better. Alright, so basically the thermoelectric effect, what is it? It's basically converting temperature differences to electrical voltage, and then a thermoelectric material is basically materials that exhibit the thermoelectric effect, and we basically make these types of materials by doping, which is adding impurities to various metals. So for my research, I investigated 2 PBT nanowires, which were doped with iodine, 2 were doped with sodium, and the remaining 2 were undoped. And then also 3 of these nanowires have a rectangular structure, and the last half has a helical structure. Okay, and these are just examples. So this is a helical structure doped with iodine. Bottom is rectangular structure doped with sodium. And then now, just a brief recap as to the methods that I use for my research. Alright, so basically I did density of states for all 6 of my models, and density of states is the number of states per interval of energy, and it's basically defined as a summation of all these delta functions. Absorption, it's basically oscillator strength that is defined as the probability that an electron that absorbs a photon will shift into orbitals, and these are all the relevant equations that go with that. Okay, now for the meat of my presentation, which are the results and analysis. Okay, so the first thing I have here is momentum dispersion, band energy on the y-axis, momentum on the x-axis. As you can see for graphs B, C, D, and E, they're mostly horizontal. So that basically means there's a minimal dependence on the band energy with the momentum. However, for graph A, you can see that there's a strong linear dependence of the band energy with the momentum. And if I had more time, I would investigate that. And that's one of the questions I plan to investigate going forward into my research. Okay, and this table here is my density of states. As you can see here, the two undoped graphs here in this column have the smallest band gap. And then the Na doped nanowires here in this column have the largest band gap. The I doped helical has the smallest band gap. And for this one, I know like this isn't the right graph because it doesn't have the HOMO and LUBO orbitals. So I apologize for that. But since I was running out of time, I just wanted to show you guys what I did for this. So again, I know it's quite right, and I'm really sorry about that. Okay, and these are my absorption spectrographs. So in terms of time, I just wanted to briefly show you guys this, and I'm not going to go over them too much in this presentation, but if you guys have any questions about this, you are welcome to ask me. All right. Okay, now for the conclusions. What conclusions can we draw from my results? So to recap, the purpose is to find out if PBT nanowires are good materials for semiconductors. The absorption spectra, density of states, and momentum dispersion for 6 of these models were calculated. So it appears from my all the research I've done that the sodium doped PBT nanowires are the best material due to their band gap. However, more work is needed. So if I had more time for my research, I would have incorporated heating and molecular dynamics into this. And then the absorption spectra for the IOD doped nanowires has to be verified. And again, I talked about the density of states for the I-doped rectangular. That also has to be looked at because that didn't show the HOMO and LUMO states. And that concludes my presentation. Thank you, guys.
Paper is open for discussion and questions. I can start. To which temperature you need to heat your sample in order to promote electron from HOMO to LUMO?
I'd say around 1000 Kelvin.
Okay, yeah, it's reasonable.
I have actually 2 questions. One is just based on your introduction where you were talking about doped, not doped, and P with positive charge ions and negative charge ion. So what's the reason to dope? What exactly is the reason behind this doping?
We wanted to dope because the process of doping a material makes it a better material for semiconductors.
What's the physical reason?
Okay.
Any physics behind it? What really makes it better material? What processes? What properties?
Okay, so basically, these thermoelectric materials have thermoelectric properties. So basically, the temperature differences between the junction where the wires meet makes like an electrical voltage, and that electrical voltage allows for electrons to pass through.
And what's the role of the doping?
It allows for that entire process to happen.
This will not happen if there is no doping?
I mean, this will happen if there isn't doping, it's just that doping makes the entire process better.
And the second question is, so you were talking about thermal electrics, right? But then you show in absorption spectra, and you talk about absorption of light. So I'm completely confused why light is involved into this discussion at all. Like why you need to absorb light with thermoelectrics.
Okay, so I did like 1-2 weeks of research on this. So basically, I just wanted to show you guys what research, all the research I had going into this. So
in other words, it's not really connected to thermoelectrics.
So just systematically studied everything you can.
Yeah.
I see. Okay.
Last question, but very quick.
Okay. So you want to study more with the iodine dope system, but I'm just wondering why you choose iodine dopes, because the band gap is very small, like 0.03 electron volt, or even certain momentum is become close band gap.
I'm sorry. Can you speak up?
You want to study more about iodine dope, but I'm just wondering why you interested on iodine dopes, because band gap is very close. At certain momentum is also become close band gap, become metallic.
It has to do with the KT. It has to do with the KT efficiency of the thermoelectric devices. The closer it is to a conductor, the higher the KT value can be.
It's very close to the KT value, like 0.03 electron volt, and also at 0.4 momentum, band gap is closed already. It become like metallic.
Right. So as I stated in my as you've seen in my density of stage graph, the iodine doped helical structure has a very narrow band gap. So for that reason, it's probably likely going to be ruled out as a thermoelectric material. But just for the sake of really verifying that, I plan to do more work with the molecular dynamics on that structure, basically.
Good.
Okay, let's thank Kevin once again. If the audience has additional questions about thermoelectrics, maybe the next speaker, Altenburg, will be able to answer them.
Okay.
So he asked to pass this toy around.
Yeah. That was I guess I tried to look at the complete thermoelectric diode, and what's being passed around is a 3D printing of the device that I actually looked at here. So what is a thermoelectric generator? Across the temperature gradient, it converts thermal energy into an electrical charge. The higher the thermal differential can be, the more efficient the device can be, increasing your Carnot efficiencies. Although historically they've had quite low efficiencies, KTs of 1 or 2. The highest I was able to find any research on was a KT of about 3.15. So with the KTs around 2, that's about a 10% conversion efficiency. The model which was actually studied is 2 lead telluride nanowires with a 38 atom gold nanoparticle as the center junction of the diode. You'll notice how this differs from a normal photodiode or photocell, and that you actually have to have a separation between the 2 particles, or between the two nanowires. And normally you would heat that center metal piece, which would actually drive the 2 dope structures then into a positive and negative state, and that's where you get your voltage from. So the importance of the doping is to bias the circuit as it's heated. And I wasn't able to actually look into the true effects of it, but gold has some weird effects in a thermoelectric device. And then it's a noble metal, and it can act as both it's known as a noble thermoelectric metal, so it can act as both a P and N material, which helps drive the voltage differential in the device overall. In the actual image here, what you're looking at, where's my little laser? Oh, a little bit fuzzy. So the actual doping, it's two sodium atoms and 2 iodine atoms. And you can see the sodium here does not have many electrons, and the iodine decided to collect quite a few electrons in a larger orbital. So you can already begin to see the biasing of the device. And this should be the electron densities in the ground state for that specific image. For charge transfers, I really wish I would have been able to get the HOMO LUMO and actually get all these images for the system when it was heated, and then go beyond just a couple above and below HOMO and LUMO to actually demonstrate what happens with the gold nanoparticle. But you can already see bouncing around the HOMO and LUMO, how the charges in the electron orbitals transition from the N to the P material. So across that gradient, you're going to have different parts of the structure just hovering right around what it would need to do for the electron to pass from one orbital to the other orbital. The orbitals shown here is 928, 929, the HOMO orbital, 930, 931 LUMO, 932, and 933. I guess I can briefly go over how the charge transfer would actually kind of occur. So as you heated the gold nanoparticle, so if you had an arrow over here, it would be hot in the middle and then going towards cold. Heat the gold nanoparticle, and then you'd see an electron pop over from the P material, to the N material. Oh, and I guess one last thing to note on this model is also you can see the two doping atoms per nanowire. Blue should be iodine, and sodium should be the kind of light blue green atom. What was learned from heating? We did see a change from the ground state to the heated state. Of course, I actually want to show. Oh, you can't quite see it, but we do get more clearly defined band gaps, which indicate the system is more than likely doing what we need it to do and actually develop a differential charge in the heated state. And as you can see from Kevin Gima's work, the HOMO or the band gap energies shown here are more in line with the gold nanoparticle than the actual individual components of the system, which I would have needed to get into Kevin Gima's work to actually derive like what would be the voltage potentials, and get to other specifics. Great. Then, do you want me to show it blowing up? Okay. Let's see if it. Okay. Okay, so this is at 3.2 angstroms. It wasn't as interesting, but you can very lightly see the molecule beginning to completely fly apart. The temperature which was studied was 2600 Kelvin, which was well above the melting point of lead telluride, which is approximately 1197 Kelvin, and the gold nanoparticle, it's actually kind of weird that it shrinks a little bit. So, future work would be generate the orbitals for the heated system to actually show the charge transfers, if possible, get a thermal gradient across the system, and observe it over time to see if we can actually see the orbitals showing the electrons jumping around and generating a charge. Update and redo the density state and spectrographs to show more pertinent information. Keep the system to a variety of temperatures and actually find out at which point it begins to fail or show unusual properties that we aren't expecting. Running the simulation of the individual components, that was a portion of Kevin Gima's work, and if I had more time to actually flesh out everything in the written report and flesh out this presentation, I could have given you, based on the Fermi energies, the voltage potentials that you'd expect of the system at a given temperature or given temperature differential. Oh yeah, and then one thing I'd also like to do is look at different models and different doping concentrations, and finally, obviously, build an actual system to verify the computational results. So my conclusion for this semester is for the studies required to actually determine the true viability of this system as a thermoelectric generator.
Okay, let's thank you. So, any questions about thermoelectric?
Why did you heat it to a 2600 Kelvin?
It was more or less an arbitrary temperature at which we knew things were going to blow up, but it would also amplify any of the effects we were looking for in the density of states.
Are you sure this system can exist at 26?
What I was the other video I wanted to show you was the bond lengths at 3.2 angstroms, and at that one you can evenly see that everything begins to fly apart. So the system will blow up by 2600 Kelvin. The highest stability I could expect out of it would probably be right around that 1000 to 1100 Kelvin, and the actual maximum thermal differential the system can handle at this size, I don't know what kind of thermal differential it could handle. The thermoelectric devices you can buy these days, normally the thermal differential is about 300 degrees Kelvin, and if you go much more than that just because of the physical sizes, the expansion and contraction of the device across the dial will begin to break the lands and the contacts.
One more question.
Please. Yes, please.
What's the definition for the bandgap?
The definition of a bandgap?
Because your band gaps are very, very small. Almost zero, right?
Yes, they're almost.
So then.
No, can it be negative?
Yes, my knowledge is a little limited on band gaps. I've looked at this very specifically into this. I don't know if you can have a negative band gap because
the gap means the
distance between
something. Can distance be negative?
Distance could theoretically be negative if the orbitals were intersecting, but then that would be a new orbital, wouldn't it? No, it can't be negative.
Is there a band gap in metals?
It should be zero in a metal, or very close to zero in a metal.
Now you can answer the question. Can it be negative?
No, it cannot be negative.
Yeah, so the smallest band gap is in metallics. It doesn't exist there, right?
And that's why the band gap is looking kind of funny on here at approaching zero, because that was pretty much the band gap I would have expected to see for just the gold particle itself.
Okay. If there are no more questions, let's thank Kurt once again. Next presenter is Nathan Walker. His talk is connected to previous two in a sense that he also have P&N doping, but he will speak of more conventional material, silicon.
So my project this semester was to study study charge transfer in a heated p-n junction. So to start off, I have a diagram here that kind of shows you how the what the photovoltaic effect is. So if you have a p-n junction, what can happen is a photon can come in and excite an electron in an occupied silicon orbital up to an unoccupied state, and a previously unoccupied state, and that leaves a hole behind. And through non-radiative processes, that electron can decay down into the, in this case, a phosphorus atom, which is an dopant, and the hole that was left behind can transfer over to the aluminum or P dopant. And so that's pretty much what I'm trying to see with my study, to see some sort of indication that there's transfer of charge, negative electrons, over to the N dopant. And these, to start off with, I had 4 different models. Up in the top left here is undoped silicon. Over here I have just a p-doped model. There's 4 aluminum atoms throughout the structure. Down here I have an N-doped model, 4 phosphorus atoms, and down here is the p-n junction. that has 2 aluminum atoms in the middle and 1 phosphorus atom on either end. And I calculated the electrical properties using a density functional theory as implemented by the Bsb software package. Basically, it just solves a set of CHEM equations for the CHEM orbitals and their corresponding energies. And once you have those, you can calculate the density, total energy, orbital absorption spectra, and density of states. So before I heated the PN junction, I calculated all of the density of states and absorption for all 4 models. Again, this diagram in the top left is the undoped silicon, and then you have the p-doped, n-doped, and the co-doped model, which is kind of blocked. I'm sorry about that. But you can see that there's a band gap in each of the models, which is it's what I wanted to see. Showed me that nothing terrible went wrong. And in the case of the p-doped, there's some empty valence band states, and in the case of the n-doped model, there's some occupied states in the conduction band, which again is what I'd expect. And you can notice that the band gap tends to decrease when you dope it, which is also what you would expect. And here I have the absorption spectra. These seem to agree well with the density of states that I just showed you. There's no transitions at energies where transitions would be forbidden due to the band gap, and peaks correspond to what appear to be permissible transitions, also from the density of states. And here I have visualizations of the orbitals, of the frontier orbitals. In this picture, the red represents the HOMO and the blue represents the LUMO. As you can see in the undoped model, the orbitals are unlocalized. They're spread out throughout the entire structure. You can see a similar thing with the p-doped model. It's not quite as smooth, but it doesn't seem to localize around any particular dopant. Then with the n-doped model, you do see a little bit of localization, probably due to the fact that there's occupied states in the conduction band. And then with the co-doped model, you can clearly see that the HOMO is localized around the aluminum atoms and or the p-doped dopants, and the LUMO is localized around the n-dopants, which indicates that charge transfer could take place going from the p side of the PN junction to the n side, which, from what I told you earlier, is what I was hoping would happen. And after that, I heated just the PN junction, and I ran molecular dynamics. This plot right here is just the temperature plotted as a function of time. There are some oscillations, but the fact that they all oscillate around an average of 1165 Kelvin indicates that it's in thermal equilibrium. And over here you have the density of states. What's kind of odd about that is that there's unoccupied states in the valence band. So in that sense, it looks kind of like what the p-doped model looked like without any heating. And I'm not entirely sure how to explain that, but it's what I found. And over here is the absorption spectra. Again, it seems to agree with what I see in the density of states. A sharp peak up here that could occur due to transitions in here. And there's lower points that correspond to forbidden transitions, and then things kind of go up from there. And then here I have a visualization of the orbitals of the PN junction after heating. Again, you can see that there's localization around the different dopants, but in this case, the HOMO is actually localized around the n-dope, and the LUMO is localized around the p-dope. At first, I was not entirely sure how to explain that, but what I tried doing, unfortunately, after I put the presentation together, was I looked at the LUMO +1 and the HOMO -1 and plotted those orbitals. And what you see is actually the reverse of this. The HOMO, like before, is localized around the P dope, and the LUMO is localized around the N dope. So it could just be that since the energies are pretty close to each other, when you heat it and run molecular dynamics, there's some kind of switching back and forth between the different energy levels. But between this and the fact that earlier there were empty valence band states kind of makes me want to study this further and verify any of this. And to top it off, I have a video of the molecular dynamics. It shows that at the very least, at this temperature, the p-n junction doesn't want to blow up or fall apart. But that's all I have for you.
Okay, that's fine, thank you. Paper is open for discussion and questions. I can start just to warm up. So, in case you would have infinite bulk, and you would have only one dopant, like phosphorus or aluminum, what is your intuitive expectation or experience based on your simulation? Would orbitals contributed by these dopants localize only on the dopant atom in the tiny vicinity, or delocalize very broad?
I would think that they localize around any dopant. I think that they'd localize around a dopant, but
how far do they sit on the near silicon atoms as well?
I'd say they probably sit near on the silicon atoms near the dopant as well.
And what would determine how far they can protrude?
How many extra electrons or holes the dopant has.
So it would be Coulombic attraction.
Yeah.
Okay. More questions to Nathan? About
yes.
So can you go to your figure with absorption spectra at 0 Kelvin for 4 cases, right? You are showing me.
Absorption spectra for 0 Kelvin?
Mm-hmm. This one, I guess. Yeah. So your first peak in the undoped system, right, is more than 1.5 electron volts.
Yep. While
the gap is less than 1 electron volt.
Yep.
So how can you explain this? Why your absorption spectra is much larger than your band gap?
So if you look here, the absorption spectra depends not only on whether or not a transition is allowed, but also on the oscillator strength, or that whether or not there's an open state for it to jump to, but also the oscillator strength. And
no, the energy of your transition is exactly, since you don't have any introduction of the Coulomb interaction between your electron and hole, then the energy of this jump from electron to hole state would be just the energy of your ground state orbitals occupied minus energy of the unoccupied orbital. That's it. So then it should completely correlate to your band gap, but it doesn't. So you're saying it's because you probably were on the right track. I think I didn't really catch what exactly you're trying to say.
So I was kind of pointing towards the oscillator strength.
So what happens with oscillator strength?
It depends on the dipole moment and the dipole moment matrix elements, and if those are forbidden.
And so these low transitions, HOMO-LUMO transitions, are not optically active.
Yes.
Is it reasonable? What do you know about silicon?
It doesn't seem completely unreasonable to me, but
silicon is known that it's not really meeting light, and it's well, we say it's not direct band gap semiconductor, so actually low transitions would be not optically active.
Okay. All right.
More questions to Nathan? If no, thank you once again. And the next presentation by Benjamin Jeffrey is connected to a previous one by the fact that they both are working on charge transfer.
Okay, so my name is Ben, and I'm going to be presenting on the effect of heat on the properties of a cadmium-selenium quantum dot attached to a ruthenium bipyridine complex die. So to explain a couple of those words, a quantum dot is a small nanostructure. In this case, we are using cadmium-selenium-based crystal structure that is formed into a small dot. In this case, it's 66 atoms. And then we have ruthenium bipyridine complex. We have a central 2+ ruthenium surrounded by 3 bipyridines, in which the ruthenium is complexed with the ruthenium. We also have a few attachments to the bipyridines, like a non-protonated carboxylic group to attach to the quantum dot. So to look at what I did, I started with the system. I calculated the optimized structure, found the density of states in absorption spectra, then I heated the molecule and subjected it to molecular dynamics, and then I recalculated the density of states in absorption spectra. Pretty simple. I heated it to 2000 Kelvin. I don't know if it actually got to that temperature, but that's what I set it to. So here's the initial system. Here is the cadmium-selenium quantum dot, with the cadmium being this purple and the selenium being this alien green, I guess. So then we have the bipyridine ruthenium dye. We have the central ruthenium. We have the carboxylic group attached to the quantum dot. And then we have a little methyl group attached to the bipyridine as well. So we have the density of states in absorption spectra, which is obscured, but this is the important part of the absorption spectra. So we have density of states. It has been pointed out to me that this density of states has the wrong occupation, at the very least, because this is for a neutral system, and so it has stuff in the conduction band. Yes, the conduction band. But the important part is there's a band gap, and the important part is there's no stray state. There's no stray absorption in the low energy states. So after we heated it, we get some breakup of the dye. The bipyridines broke quite a bit, but the quantum dot didn't change all that much. Density of states changed quite a bit. Most notably, the band gap is gone. We don't have a band gap. And there's some stray low energy states in the absorption spectra, which I'll talk about what that might mean a bit later. So here we have the dynamics. It's pretty short, but it's all moving around. Quantum dot, like I said, isn't doing a whole lot, but at least one more. Okay, it doesn't want to cooperate, but the dye has quite a bit more movement, and so we come to the conclusions in comparing the final structure to the initial structure. We see that the quantum dot structure doesn't really change drastically. However, the dye broke some of the bipyridine rings. The band gap closed, making the system a conductor. This would disrupt the lifetime of any charge transfer states, which is the entire point of the cadmium-selenium dye system. I guess I didn't mention that at the beginning. That was the entire point of the system. And then the absorption spectra shows several low-energy, optically dark transition states, which isn't particularly what's the word, healthy, I guess, for the system. So, and I would have liked to actually show orbitals, but I was only able to get orbitals to work for before heating. After heating, it just refused to print hard charge files. So here's what they look like before heating. We have definite signs of charge transfer, which is what we're looking for in the quantum dot die structure. So,
but this is with the wrong charge. You already charge your system. I mean, you put 0 charge, but what should be the right charge on this system?
The right charge should be +1.
So it means you already add additional electron.
Yes.
You can think that you already have it, let's say, between the LEDs, right? Put some voltage, and you already populate the state which is should be unoccupied, right? You populate with additional electron, making system neutral, but in reality, actually, you're really adding the electron there, right? And this probably results on this kind of charge transfer character and blah, blah, blah.
In case it wasn't obvious, that is my presentation.
Yeah, let's then continue the discussion. Yep, Professor.
I'm just curious, is there any logic behind the size of the quantum dot you choose?
I think the logic was
What is the size?
mainly, it's a 66 atom.
In nanometers. Can
Oh,
you tell?
nanometers. I don't actually know. Is it half a nanometer?
Oh, it's small. It's more than 1 nanometer. It's 1.5.
Oh, 1.5. Okay.
Same order of magnitude.
But yeah, about 1 nanometer in size. Yeah.
I think the logic was that it wouldn't be too computationally stressful.
Have they ever made this an experiment?
This system?
The quantum dot.
By the way, he knows the answer.
I don't know. You asking the question would lead me to say no?
No, they've done this in experiment.
Okay.
The regular size of quantum dots people are comfortable to work is from 2 nanometers, right, up to 4 in this range. This is typical range of quantum dots where they're really interested in quantum effects and confinement effect, right? So our system's a little bit below this, but experimentally they call it magic size quantum dots. People were showing you can create such quantum dots. It just requires more sophisticated approach, and it's much easier to synthesize and work with a little bit larger size, right? But it's a few nanometer size systems, which is reasonable kind of size, and again, reasonable in terms of calculations because you're spending time. I mean, you're not spending a lot of time.
So what temperature did your organic molecule end up breaking?
Like I said, I set it to heat to 2000 Kelvin. I'm not positive that it reached that height. VASP wasn't very kind to me during this, so yes, in theory it reached 2000.
What is the temperature?
Well, you said the molecule broke, right? I just want to know at what point it broke.
Not really. Completely broke. Just very
Looks
significant.
like
Just some range.
oscillations of very high amplitude.
Yeah. Just very last question, based mainly probably on a course which you were taking with me last year, right?
Okay.
On the thermodynamics. So first question is, you treat, what do you think? You treat, when you heat your system, you treat these vibrations classically or quantumly? Well, how do you, well, electrons for sure you treat quantumly. You need to solve Schrödinger equation or whatever, Kansham equation. What about vibrational, which means atomic motion, right?
I don't know for sure, but I'm gonna guess classically.
Okay, yeah, classically. And now, if you remember, in thermodynamics, we were comparing temperature with rotational, vibrational temperatures of specific molecules, right? And what do you think the range of these vibrational temperatures for organic molecules compared to your 2000 kelvins? Large, small, comparable? Like if you think about CO2 molecule, right? Or kind of CC stretching, CO, CN bonds. What would be the range of temperatures, what we call rotational vibrational temperatures based on the vibrational modes?
I'm guessing in the hundreds of Kelvin.
Oh no, they are in the thousands. Hundreds would be for your quantum dot.
Oh.
For heavy molecules, it would be in the hundreds, right? For light molecules, it would be in the thousands. So technically, getting to these large temperatures, you're really putting, or trying at least, reaching this vibrational temperatures, which put it more or less close to the classical regime for the molecules. And of course, you're in a classical regime for the quantum dot because they are much smaller frequencies, vibrational frequencies for the inorganic materials. And again, this might be the reason why you heat it and why you really see this molecule is really making this motion, because this is really huge temperatures where these vibrations make an impact.
Okay, let's thank Ben once again. So, next presenter is Gary Schmieder, and his talk is not connected to anything we've previously seen. It will be drastically different because we start a new chapter. So please make yourself comfortable to dig into coolers for ice cream or coffee supply and thermos in the back. Okay, floor is yours.
Okay. Before we really start getting into what exactly I did, it's rocket fuel, so. Nope, that's not supposed to happen.
Dr. Tillin, can we leave that off all the time?
There we go.
No, so keep it this way.
So, for context, this is just a Falcon Heavy test flight.
Nice.
I'm not entirely sure that they were using this type of rocket fuel yet. That's what they're going for, but this is more for a visual aid than a accurate representation of what this is right now. This is what they want it to be. So, Methalox is just a liquid oxygen and liquid methane rocket fuel. The reason that we're looking at this as a potential fuel now is it's a lot easier to store on the rocket itself. It's doesn't boil it boils at a higher temperature than liquid hydrogen does, so you don't have to use as much energy to keep it cool. More dense, you can get it in a smaller package. It does have a lower specific impulse, so you're not getting as much thrust, but that's kind of canceled out by the weight you're saving with the storage stuff. So when it burns, ideally it's doing that. Move the.
But everyone has books.
Okay, yes. So basically, the camera is covering up what we want to happen. Because if it goes through this reaction pathway, it's basically just. Okay, I forgot the.
Carbon dioxide.
I was going to say hydrocarbons. I don't remember what the P and A stand for. But that's just an incomplete combustion, and for a rocket fuel, we don't really want that. We want it to keep going. So we have to find out what set of conditions will produce us going along this particular pathway where that's. So what we've done is this was all run through VASP. We're setting up the initial electronic structure with that. At each time step, we're applying the temperature variable, which as low as 300 up to, I think we got up to 3,000. And at each point we're, well, not each point, but we're testing the molecular dynamics to kind of see how the system is behaving under these conditions. So running it at 300 Kelvin, the system doesn't really do anything because that's just a low temperature, it's not going to ignite, and not terribly responsive. At 3,000 Kelvin, it just basically decomposes and does nothing because we've passed the point where it's actually viable and it just. So we have to find something in between. I'm not going to go through the entire how that's figured out. Just trust me that this was the one that was actually good. So at 2400K, we see here the temperature is actually 3000 pretty much immediately, and it continues to rise. So it's kind of an indication that there was ignition. It did what it's supposed to do. It's kind of self-sustaining now. Of course, this is a very short time scale to really say that. Running it with spin polarization calculated, actually get a longer time scale and a little bit higher temperature here, so there's just more data, really. For the energies of those, again, they kind of show a similar. They're similar to how these two are. 2400K, you get results. 2400K with the spin polarization, you get better or at least more defined results. So basically, again, that's being covered up. So it's kind of just, this is the, as we, this pointer. So we can kind of see it traveling through, and you can't see that. You can see it traveling through this pathway to some degree when we're looking through these images. So this is it at the start. It's reacting with the oxygen, with that intermediary, and then that you can see in the paper. Which light switches do we want?
Just start this one.
Okay. So this is basically just an animation of what it's going through in the previous slide. You can kind of see, this methane is a good one to focus on. It was central. You can see it interacting with the oxygens and then losing it. Here we can actually see at which points in that reaction these stages are. So we have, get the colors right. So that's B, that is C, and then D. So following that, we can see that we're on the right pathway, and then it's going to end up in the proper combustion stage. And here we can kind of see how the distances between these atoms are, or I guess the bonds is a better term, how these are, the trajectory of these through time. Important to note this is a much larger time scale than what we have for the molecular dynamics stuff. Or no, smaller time scale, sorry. That doesn't mix up. So this is basically happening instantaneously compared to the other graphs that we saw. I don't remember this. Kind of seems like a model afterwards. Oh, it's a video. Yeah.
Okay, but thank you. So, paper is open for discussion and questions.
So you have figure 2 showing this dependence of total energy on spin state, right? The multiplicity of the system. So can you explain a little bit more what exactly is the role of this multiplicity? Why is it not, like, we usually think that in a ground state most of compounds should have they're in a singlet state, right?
Yeah.
In your case, you have really very high multiplicity, and the lowest energy is at multiplicity equals 6. I even don't know how you call this state. So what exactly is the reason for this multiplicity?
believe this was based on like how many we had in the system, right?
How many of what?
Because the system is.
You don't show this image in your presentation. It's only in your.
No, I'm just saying that this. We're looking at 4 methanes, and I believe that's 8 oxygens.
Uh-huh.
I believe that's what's causing the. You're kind of multiplying it by that, I believe, is what.
So what's spin multiplicity of oxygen in ground state?
I believe it was singlet.
Huh?
It's an exception.
Right.
Oxygen is an exception.
Anyone in the class? What is the multiplicity of oxygen in the ground state?
Yes.
Who told us? Okay. Plus 5 points. And if you have like 6 or 8 oxygens in the model, then the multiplicity would be much bigger. So it's liquid oxygen is known to be magnetic. One can just pull it from that bucket with a magnet. More questions to Gage? More questions 1? More questions 2? Okay, well, thank you once again. So, we are continuing journey into the chemical reactions, and next presentation will be by Mermal Hedrick. So she will present on polymers.
All right, good.
Polymerization, right?
Yes. Good evening, everyone. So my talk is derived from my work I did at Boeing. We worked with proprietary materials that we really didn't know what was causing it to fail when we would coat our substrates with epoxy, and we were finding that when we subjected them to water, we were getting TG to go up, which told
what
us
is TG?
Glass transition.
Can you speak louder? A little
sorry.
louder.
So, in a polymeric material, if it's doing what it's supposed to, you know, if you expose it to water, you know, it could plasticize or those kind of things. But my TG was going up, which was showing that my epoxy was becoming more brittle. So it was really hard because we didn't have a chance to do formulations or experience any of that because we have patents that you have to kind of navigate by. But a way to go through this was a computational study, yes?
Before going further, just for all audience, what is epoxy? And if it is shown on the slide, you may...
Yes, sorry. To get into our epoxy here. So this is a very simple example in real life of how we create a epoxy primer. So we start with our we start with our epoxy and then our amines, and they go ahead and react to make this nice cross-link system. So when I say epoxy primer, it's a cross-link system, and it has a TG. The TGs are usually pretty high, around 60, but with our system, we were finding it to dip below. So the question remains, will we see a difference if we add water into the system? And will our molecular dynamics give us a case that, yes, something is changing, it's interacting with water, so you might be having something happen that you didn't expect would happen. So the goal here was, again, to understand what happens, how TD changes when we expose our system to water from our experimental tests, but shown in our simulations. And to do that, we used Bsb to initially do the optimization, and then we did molecular dynamics to look at it in a heated system. And we wanted to determine whether there were notable changes from dry and wet simulations, wet meaning the addition of water. So we used a Vienna ab initio simulation package, and we did the molecular dynamics with the heating. And the goal of the high temperatures was, well, we know that if we use real life temperatures, that's fantastic, that's great, we can figure out that our system will work. But if we heat it up and see if it still stays together, it'll be interesting to kind of see, you know, we know in real life it wouldn't exist necessarily because it's going to degrade, but maybe it'd be interesting to look at the physical interactions or what happens. We used a PBE functional plane wave basis at pseudopotentials. In our cell, shown here, this is actual measurements of our cell. So it's a 14 9 by 9. Originally had 288 atoms, and again, we have our amine hardener, epoxy, and our water. You can see that shown here. And the density that I'm showing that I calculated is actually not too bad. So it means we don't have too many atoms or too less of atoms in our system. And why that is because epoxy in real life is 1.2, and I got 1.6. Pretty comparable. I would say this looks like it's an epoxy system. And then to see how it behaves in kind of a smaller cell and with heat, we did a reduced cell size, then we did that with molecular dynamics. For the equations, we used as was discussed earlier for the electronic structure here, we have our Hamiltonian and we're looking with our Kampschal. Orbitals for the density of state is the summation per state, and then our absorption is looking at our oscillator strengths of our different transitions. So, the real meat of this presentation comes from the interval at which we can see everything interact. So the idea is that we look at this system and we kind of take a snapshot of any point in time to see, are we indeed forming these bonds where we see the epoxy break up and we see some sort of connection with the amine hardener.
Because very hard to see anything in this picture, so many atoms. So your initial structure actually is a polymeric material,
yes,
or like your initial...
Is it before or after polymerization?
Yeah. This would be after. So, oh, no, this would be before. Sorry, this would be before.
So can you just point by finger on the board telling what are
of course.
Reactants or precursors?
Okay, so this is going to be our carbons.
No, molecules, names of molecules, not atoms.
Sure, sorry. Here's the epoxy, here's the amine. The nitrogen is going to be your amine system, and then the epoxy is going to be the red, but there's also water mixed in there. So that is what...
So how many epoxy, how many amines in simulation cell?
Well, in the original one, I mean, well, I don't remember exactly. I know there was 280.
It looks like you should have 4:1 ratio at least, right? You have, on your scheme, you need to have 4 epoxy to 1, wherever this amine group, right?
1 to 2.
Looks like 4. 4 to 1 to get this polymer, because you have these groups.
Well, I see 6.
But your goal is to see whether you will be able to get a polymer from it.
Yes.
Right?
So let's see.
Is it image or... Oh.
There we go. Sorry, I had to press the next button. So we can see, this is a good example. I don't know if you guys can see it, but right there, you start to see that epoxy. Aha, there it is. It's really quick, right in the middle. It starts to break up.
So which bond is breaking up?
The epoxy.
Which bond between which?
Oh, the oxygen carbon.
Okay. Why it is breaking?
Heat.
Would it break without water?
The reaction can occur by itself. The amine acts as a neutrophile and attack the epoxy ring.
Have you done these calculations without water, just in vacuum as well?
No.
Just with water. But I think the question is, if you don't have water, would this breaking of the bond happens in your simulation cell?
Yes, it can. You can just mix the 2 components.
I mean, in experimental conditions, it happens without water, but you didn't really check. Okay.
But this looks like it's breaking up not towards the amine, but towards another epoxy.
Well, it's like a multi-step reaction.
Okay.
Okay.
But amine can't be close.
But in this case, you were using heat, right? You were just heating it up.
Okay, so going forward, oh, okay, well now we see both. All right, so this gives us a nice snapshot of the MD and heat. So I just kind of showed every 10 time steps, I guess you could say. And if you follow here, you can see, okay, you can see there, well, there's some bond distances we have, indicated here. And then between the oxygen and the carbon in epoxy, it starts to increase every 10 time steps. And then you can see it looks like it's split. And this shows this is covering it up. You can see it's roughly around 2.3 angstroms. And then the last one, this blows it up kind of nice. You can see it's 2.23. And the angle is, in the epoxy has increased. Did I? Oh yeah, I went the right direction, okay. So again, this.
Is it an image or video?
Here we go. So this is with a few more steps. And it's so busy, it's hard to tell what's going on. But we could see the epoxy kind of just breaking up and kind of interacting with itself.
So this is high temperature?
Or is it just longer simulation?
I believe it's just a longer simulation. So, nope, that was just that one. Oh, I messed it up. Hold on. Aha! Come on this way. Okay. Yeah. So you could see that the hydrogen is being shared between the amine and the oxygen. So it seems it's interacting, and if we let it run for a really, really long time, maybe we see everything perfectly form, and then lead to something like this.
So it's not full polymer, but some partial polymerization.
Yeah, so some oligomerization is happening there. So to see if, well, are we indeed interacting, we have our homoluminal orbitals. It's hard to tell where's what, but we see some charge density around the oxygen. So it makes me think there is some interaction happening there of some kind. For the total density states, we just did this was our simple case where we didn't have the heat, we just started out with VASP. Our left side is the vacuum, and this just shows this where we see our orbital energy in our bandgap. And what's interesting is when we add the effect of water, we see that our energy goes down. So this could be interesting to look at the binding energy of the system. We could see I did confirm the total energy when we added the effect of water. So vacuum is without water, and the water is the epoxy plus water. So vacuum is epoxy. And so it'll be interesting to see if that is indeed the case. If I were to run water by itself and calculate the binding energies of the epoxy water contribution and see if that was the case. So it looks like it's stabilizing with the effect of water. So it could be that it's relaxing a bit. So the absorption spectra is, okay, well, are we indeed forming epoxy? And shown here from experiments, epoxy is about 300 to 350 wavelengths. And then we look up here, yeah, so our peaks correspond quite nicely. So what the material we're working with has epoxy characteristics, and that's useful to make sure we're starting with the right material. So what I mean by the charge system, so we have our neutral case, and this is an MD, and this is also for a reduced cell size and less atoms. What we can see is we want to make sure, okay, are there any kind of like radicals in our system? How does our density of states and spectra change if we just kind of add some charge or delete some charge from our system? And it shows here it's kind of like your reference point. if we kind of add anions, add electrons to the system, we see that, yes, we have some presence of our occupied states here, but we also see that the band gap goes up a little bit. So it makes me wonder, I don't know how stable that configuration is. When we look at the cation case, when we actually take away, we start to see the shift goes up a little bit, but it's still kind of comparable. So that might be a favorable case. There might be some, or maybe some radical in there, there may not. So maybe most likely the neutral case is pretty happy. When we look at the spectra, it's really interesting because they all look really the same. So at least for the first case where you have a negative charge, like you could do each interval, we see, you know, they're about the same. If we went further deep, added more charge or subtracted more charge, we might see some changes. But we have to examine those. So the idea from this is that we wanted to show that degradation does occur with excitation of the molecule. And the excited state shows high absorption in the UV range, which correlates with the high energy. Bond breakage location correlates well with previous work, and ability to recycle the building blocks. And we need to figure out more to see how the polymer forms with the presence of water. And if there's any kind of thing to suggest that it is some parts are breaking off where we're having material leach. So.
Okay, well, thank you. Is it 2 questions? We had some discussion, but maybe someone has steam to get more insight into polymerization processes.
There's one question regarding the dry and wet dose spectrums. So you said in case of the wet one, it's getting more stabilized, right?
Mm-hmm.
But if you take a look at the bandgap, it actually gets smaller. It means kind of less stable system, right? And bandgap gets smaller, it's kind of more reactive, less stable. Or you have some other opinion about that?
It may. That I didn't really explore the thought into that, but since we're dealing with a polymeric system, you know, we're not working with what other folks have worked on in terms of quantum confinement and any of that stuff. We'll put that to the side. We're looking at a much bigger system here and different effects. Yeah, the decrease in the band gap might be concerning a bit if we have some unstable charges running through the system or something that's not quite friendly working with together. So I think to fix this, or to not fix, to further explore, we would have to run more molecular, I think more reaction dynamics, or getting that further step process to see. Because I think initially we might have an unstable system, and as time goes on, it becomes more and more stable.
Okay, but thank you. And the next presenter is Ericsson. So his work is partly related to performance as well.
Hello. I'll make this quick. So I'll be working on, or commenting on nitrobenzyl polymer degradation. All right. So just overall overview. There's been some work done with some photodegradation on nitrobenzyl group polymers. Dr. Webster and I think Dr. Seavey, who's not here. I don't know if I'm pronouncing that name right. But they previously did some work where they built a polymer together with these nitrobenzyl groups as part of a building block, and then they put some UV light on it, and they found out it could degrade. The polymer that was used is over there. It's not blocked by the video screen, and I have a 3D version of it down here below. So just to kind of give you guys a quick overview, due to timing issues, I didn't input everything as much as the other representatives did. For example, for the excited state DOS, all I was put in was
Let me interrupt. So just very quickly, can you clarify what exactly is the goal for your simulations? To see that these bonds will be broken in a way how it was expected in experiment or what?
Yep, thank you. I apologize for not clarifying. Yeah, that is my goal, is to simulate the degradation to hopefully see similarity between the two and give a better in-depth information compared to what only these people have done. So, thank you. So when it comes to DOS, I just showed the HOMO-LUMO gap, or excited state. As you can see, there's an electron jump from HOMO to LUMO. And then I wanted to also show the absorption spectra. So this is known to degrade with UV excitation. And as you can see, in this wavelength range, it does absorb those waves. I'm not saying it's the highest amount, but that's where most of the action occurs. So also, if you really wanted to, you could shine some purple on the polymer and it would probably degrade. I do have a couple quick videos. I don't know if this will work here. Oh, I gave.
Try to click on the.
Okay. You guys can see that. Close it.
Click on the image.
Oh. So one of the things I wanted to present earlier, I actually had two of these, but even though it was the excited state, I wasn't able to show any sort of degradation, but on previous work that Dr. Killen and it was shown on my other particular molecule actually from the pentene ring, and that shows some sort of degradation that I wanted to show in this video. And now it's showing a benzene ring, but it also encompasses it, so it'll connect onto the benzene as well. Now I didn't show it graph, but it is on my that this area of the HOMO is actually around the pentene ring. I can't tell you this degradation, but that's what I said that it didn't. Oh, it's not. Not see a break for some reason. Clarification with that. Actually, previous work we just did the 500 Kelvin cycle. This didn't occur. Yes, but I was still understanding the basics of fast and other incidents, so I didn't want to put energy into this and excited and not. So that was my. I did have a little picture there. I was showing break it. मोटर गाड़ी नहीं चलती थी, घरवाली को लेने कैसे चलते थे भाई? ससुराल में कैसे चलते थे? ससुराल में तुम्हारे माता पिता ठीक होंगे करे? पड़ोसी पड़ोसी
Yes. So you already said that you expect the energy of the first absorption. Why you were 500 kelvin if then what temperature actually corresponds to?
So when we took a stab at it, we shot it at 500 Kelvin, and we just saw the little for whatever reason, I was not able to show that degradation in any other videos for some reason. Just regular, non-excited state of 500 Kelvin. So just took a stab and it worked.
Why not then temperature?
Yeah, I'm learning how to connect all the okay, I'm going to use the graph from the OS.
specific wavelength.
Okay.
Do you think that they designed to absorb at a specific wavelength to have a surface that causes elevation? And if so, would thermally exciting versus exciting the excited state?
That's a lot of info in one. Now, when you say it, the comparison of thermal excitation and just like...
So, like in VASP, you can say populate the state and then run it. Where you can say heat it to 5,000 K or whatever. Do you think populating the excited state or heating the molecule will result in physically meaningful results? Or are you just saying, I'm hitting it with a hammer and I just want to see it break?
Because I'm still understanding what the use computation. My understanding is we're going to excite it and then we're going to put it.
Wow, look at that.
Could be
He is
मंकी जेंटलमैन कुर्सी पर बैठ गए मंकी आगे चल के थोड़ा सा अपना रोग और मूड बता जरा शहर का जेंटलमैन मंकी आपका रोग और मूड अच्छा हो गया अपनी कुर्सी पर आके बैठ जाए गुस्सा नहीं करो आपकी मिन्नत कर रहा हूँ कुर्सी पर बैठ जाए मंकी माई बाप की कसम बहनों भाइयों की मंकी जेंटलमैन आपकी बेगम साहबा की कसम कुर्सी पर बैठ
If this happens, then you probably really expect that there is no really any difference.
जेंटलमैन मंकी जरा ससुराल वाले घर में जाना जरा नई नई शादी करा के जेंटलमैनों के घर ससुराल वाले घर में वापसी भी जाना कैसे बैठ जाना ससुराल के पास ससुराल के पास में आपकी इज्जत हुई चाय पानी रोटी पेप्सी बर्गर बिल्कुल कुछ नहीं मिला क्या तकलीफ हुई ससुराल के पीछे ससुराल से डरे खाना बना बैठ के बंदर जेंटलमैन ससुराल का आटा गूंद के दिखा रखा बहुत तरह खाना बहुत जेंटलमैन बंदर जरा ससुराल को गुस्सा आया मार के डंडी टांग कौन सी तोड़ दी ससुराल ये वाली लड़का अपने घर में होता था पहलवान क्लब का लाहौरी पहलवान एक्सरसाइज बहुत अमोंकी जेंटलमैन एक्सरसाइज बहुत अमोंकी जरा जंप लगा जरा पहलवान गाड़ी बना जरा मोटरसाइकिल कैसे गाड़ी जा रही है जना सुपर शॉपिंग के खराब होगी बार बार बाजार कैसे जा रही वर्कशॉप गाड़ी का पागल हो जा बंदर नशेदार दीवाना बहुत सारा पागल मोगी जेंटलमैन गन का निशाना लगा जरा दुश्मन के भाई जहाज को जरा दुश्मन को जरा देख देख के निशाना मोगी जेंटलमैन जरा निशाना बैठ के लगा दे उठ राइट गुड मैन उठ के बैठ के उठ राइट गुड मैन उठ के बैठ के उठ राइट गुड मैन गोली लगी और मर मैन मोम के साथ दुश्मन आ गया मोम से और आगे चलो भाई गुड तुम भी जरा 2 मिनट के लिए सामने आ गुड जरा बेज़बान जानवर हो वान माला इंसान इंसान के बच्चे को पढ़ाना बहुत मुश्किल की बात। बेज़बान जानवर और ज़रा 2 मिनट के लिए ज़रा चक्कर लगाओ और चक्कर लगा के ज़रा बता, और चक्कर लगा के बता कि सब दुनिया का और कुल कायनात का कौन मालिक है, कौन वारिस है और कौन वसीला है जो गरीब और अमीर को रोजी रिज़्क़ दे। बोर्ड ज़रा मुसलमान का सीधा हाथ कौन सा जिसके साथ लोग 11वीं कुर्बानी ज़कात और खाना सजदा करो जैसे मुसलमान नमाज पढ़ के सजदा करता है अल्लाह को, सजदा करो अल्लाह को और दुआ करो सबको जरा दोनों बॉडी में। क्या बात है जी, क्या बात है। शाबाश गोट के लिए कल को शाबाश तेरी समझ। बेज़बान जानवर गोट इंसान के बच्चे को पढ़ाना बहुत मुश्किल की बात। सौखा आइटम किया और जरा औखा आइटम भी करके छोटे छोटे लकड़ी के पाए इनके ऊपर चलो, ऐसे चलो जैसे छोटे छोटे बच्चे घरों की सीढ़ियों पर पाए छोटे और वजन ज्यादा। संभल के अल्लाह को याद करो और अल्लाह का नाम लेके जरा कैसे जरा घोड़ जरा चल के आसरे आसरे के साथ जरा अल्लाह को याद करो और अल्लाह का नाम लेके कैसे जरा घोड़ जरा चल के दिखाओ। क्या बात है जी। घोड़ पाए छोटे वजन ज्यादा, संभल के अल्लाह को याद करके और अल्लाह का नाम लेके। घोड़ जरा एक से दूसरे पर जाना मुश्किल है, जरा अल्लाह का नाम लेके और अल्लाह को याद करो जरा दूसरे वाले पाए पर कैसे चलो। घोड़ जरा आसरे आसरे के साथ जरा अल्लाह को याद करो और अल्लाह का नाम लेके एक से दूसरे पर जाना मुश्किल है, जरा अल्लाह का नाम लेके जरा दूसरे वाले पाए पर भी जरा चलो। घोड़ जरा पाए छोटे हैं और वजन ज्यादा, संभल के जरा अल्लाह को याद करके और अल्लाह का नाम लेके ऐसे घोड़ जरा चल के क्या बात है। घोड़ जरा एक से दूसरे पर चले, दूसरे से तीसरे पर जाना मुश्किल है, जरा अल्लाह का नाम लेके जरा तीसरे वाले पाए पर भी कैसे घोड़ जरा चल के दिखा। पाए छोटे हैं और वजन ज्यादा, संभल के अल्लाह को याद करके और अल्लाह का नाम लेके कैसे घोड़ जरा चल के दिखा। घोड़ जरा आसरे आसरे के साथ जरा अल्लाह को याद करो ऐसे जरा घोड़ जरा आसरे आसरे के साथ।
All the dynamics is completely frozen, and on the glass transient temperature, where one set of the dynamics start, and above the glass transient temperature, where the polymers are in the big and to understand the various
जब ट्रेनिंग देते हैं उस टाइम इसको परेशानी होती है, अभी इसको कोई परेशानी नहीं। आखिरी एक छोटा सा पाया जरा इसके ऊपर भी घोड़ जरा चल के दिखा। कैसे जरा घोड़ जरा आसरे आसरे के साथ अल्लाह को याद करो और अल्लाह का नाम ले। आखिरी एक छोटा सा पाया इसके ऊपर भी जरा चारे पाँव की जगह बनाने की कैसे ऐसे जरा घोड़ जरा आसरे आसरे के साथ जरा अल्लाह को याद करो।
And how the diagonal angles changes at these 3 different temperatures. So if you look into the density of state at 3 different temperatures, so I can say that the first temperature is below glass transition temperature is 300 Kelvin, and the one the glass transition happening
सलाम करो, सजदा करो, अल्लाह को दुआ करो, सबको जरा गरीब होके और नहीं माना।
If you see the density of state and absorption spectra, there is no
क्या बात आली हो जाओ
at 3 temperatures. Because PMMA is basically polymer. The Bandgap is almost 5 electron volt.
सलाम करो भाई। चलो मोंकी जेंटलमैन, तुम भी इधर बैठ के दोनों हाथ जोड़ के सबके लिए दुआ करो। मार दे।
This temperature there is no electronic transition happening
चल भाई अमिताभ बच्चन, पहले मैं तेरी हीरोइन श्रीदेवी का मेकअप कर दूं। हाँ, पहले मैं तेरी हीरोइन श्रीदेवी का मेकअप कर दूं बढ़िया सा जी। श्रीदेवी और अमिताभ बच्चन अब जा हो गए तैयार। लो भैया अब जा, श्रीदेवी और अमिताभ बच्चन हो गए तैयार। श्रीदेवी डांस दिखलाएगी और अमिताभ बच्चन सर्कस के करतब दिखाएगा। चल भाई अमिताभ बच्चन, जरा हमको और इन सभी बच्चों को छलांग लगा के दिखा दे। हाँ, मैंने डुगडुगी बजा दी है। चलो अब ये हो गए हैं तैयार और अमिताभ बच्चन सर्कस में लगाएगा छलांग। देखे कैसे छलांग लगाता है। आओ
मौज में चलना चाहिए, मौज में जरा दादागिरी से भैया। और कला लगाइए पहलवान साहब, सर्कस वाली जंप कैसे लगती है तुम्हारी। एक और लगाइए, एक बार कला और लगाइए। कला लगाइए, अब पहलवानी करके दिखाइए पहलवान वर्जिश कैसे करते हैं। तुम भी जरा जोर लगा के दिखाइए जोर। ये लो साहब वर्जिश हो रही है, देखो। ताली बजा दो, ताली। मौज में चलना चाहिए, मौज में जरा दादागिरी से भैया। और कला लगाइए पहलवान साहब, सर्कस वाली जंप कैसे लगती है तुम्हारी। एक और लगाइए, एक बार कला और लगाइए। कला लगाइए, अब पहलवानी करके दिखाइए पहलवान वर्जिश कैसे करते हैं। तुम भी जरा जोर लगा के दिखाइए जोर। ये लो साहब वर्जिश हो रही है, देखो। ताली बजा दो, ताली। जल्दी से लगाइए जरा कंट्रोल, और हिम्मत से लगानी है जरा वर्जिश। हाँ, बन के दिखाइए चौकीदार। ये लो साहब चौकीदार बन गए हैं। चौकीदार बन के बतलाया। अब भैया आप लोग ससुराल की तैयारी करिए, ससुराल की। पहले नंबर हरिद्वार जाके गंगा जल स्नान होता है, तो तुम भी जरा गंगा जल में स्नान लगाओ। हरिद्वार जाके गंगा जल स्नान कैसे होता है, गोता लगाओ गंगा जल में जरा। मल मल के नहाना चाहिए भैया, मल मल के जरा। और लगाइए गोता जल्दी से।
एनर्जी लैंडस्केप
भैया नहा धो गए, नहाते हुए तुम्हारी पैंट फट गई, तुम नंगे बैठे हो, तुम्हें शर्म नहीं लग रही। थोड़ी बहुत ही बेशरम हो गया। ओए बात सुन ले, बात सुन ले, शर्म करो, नेकर पहनो। तुम्हारा नेकर टेरी कोट स्टैंडर्ड नेकर है। जल्दी से पहनिए नेकर। अब जाइए ससुराल। ये लोग गाड़ी पकड़िए, डिस्कवर चलिए घरवाली को लेने के लिए। लाठी मुझे दे दो। तो नीचे नहीं बैठना चाहिए, कुर्सी पे बैठना। छोटू पन्नी तरफ ठेला पड़ा है, निकाल दिए। कुर्सी पे बैठिए, ये तुम्हारी सास ने दी है कुर्सी। ओए ये क्या बात है भाई, सास के नाम से नहीं बैठोगे। ये लोग घरवाली के नाम से बैठ जाओ, घरवाली के नाम से है? अरे ये कुर्सी तुम्हारी बड़ी साली ने दी है, उसके नाम से बैठ। अच्छा, ये कुर्सी तुम्हारी छोटी साली के घर की है जो देवबंद में रहती है, उसके नाम से बैठ जाओ। ये लो साहब, छोटी साली का नाम लिया, बड़ी जल्दी खुश होकर बैठ गई। अब हम पूछते हैं श्री देवी से, वो जाएगी या नहीं जाएगी? ए श्री देवी, खड़ी हो जाओ, तुम्हें लौंडा लेने के लिए आया है, बड़े दिनों के बाद तुम ससुराल चली जाओ। क्या बात हो गई? पूरी बात बतला। ओह लो साहब, सुन लो क्या कह रही है। ऐसे कहती है, सास के नाम से सिर में दर्द, हाथों पैरों में पीड़ा और सर में जुकाम बुखार हो गया। जाइए डॉक्टर को बुलाइए। क्यों, डॉक्टर के बस का इलाज नहीं? चलो किसी हकीम को बुलवा दें, उसके बस में भी नहीं तो तुम्हारे पास है इसके इलाज का कैप्सूल। ये बात सुन लो, लठ लग जाएगा। ये 10 आदमी बैठे हैं, तुम्हारा फैसला करा देंगे, तुम इसका फैसला मान जाओगे, तुम्हारा फैसला फिर हम, इसका मतलब तुम मानोगे नहीं है? घरवाली को छोड़ के नहीं जाओगे? अगर तुम्हारी घरवाली तुम्हें मनाने आएगी तो पिटाई तो नहीं करोगे? हैं? कभी तुम पिटाई कर दो, कहता है पिटाई। चल भाई श्री देवी, चली जा, जाने के लिए तैयार हो जा, मेरी बात को समझने तू पहुंच जा। मैंने समझा दिया, अब ये तुम्हें कुछ नहीं कहने का। और ऐसे कहती है कि जाने से पहले घर से न्यारा होना पड़ेगा। न्यारे हो जाओगे 10 दिन के लिए। यूँ कहता न्यारा नहीं होने का बिल्कुल भी। कह रही है साहब न्यारा नहीं होगा तो फैसला करके जाएगा। फैसला मांग रही है। अबे ओ बात सुन ले यार, बात सुन ले यार, बड़े आदमी बात सुन ले यार, बात सुन ले यार, झगड़ा मत करे, बात सुन। ज्यादा लड़ाई, अबे बात तो सुन ले यार, बात तो सुन ले यार, बात तो सुन ले। इसका मतलब मानोगे नहीं, छोड़ के नहीं जाओगे। अगर तुम्हें मनाने आएगी तो पिटाई तो नहीं करोगे? कभी तुम पिटाई कर दो, कहता भैया पिटाई कुर्सी पे बैठ जाओ। अच्छा, अब तुम्हें मनाने के लिए आएगी, देखो पिटाई नहीं करनी। इसको मैं नाच के मिन्नत से और खुशामद से समझाएगी। तुम टोपा लगाओ, तैयार हो जाओ। ये लो साहब, टोपा बहुत अच्छा है, लड़का बन गया है सनी देओल। सब आदमी देखो सूरत कितनी अच्छी है लड़के। भाई वाह साहब बात, भाई वाह साहब बात। आप थोड़ा सा रगड़ो अंग्रेजी पाउडर। भाई वाह, लड़के की सूरत देखना है जी, कितनी अच्छी है। भाई वाह साहब बात, भाई वाह साहब बात, भाई वाह साहब। ये लो साहब, तुम भी देखो लड़का कितना खूबसूरत है। भाई वाह, भाई वाह। अब नाचिए जरा मिन्नत से और प्यार से, ठुमका लगा के कैसे समझाती है जरा। रोक भी पार लिया तुमने तो। ठुमका लगाओ जरा मिन्नत से, कैसे मनाना है। पहलवान साहब, तुम भी अपनी घरवाली को समझा लो। लो साहब मना रहे हैं, मान गई तुम, कितने खुशी, कितने राजी, कोई गुस्सा, हाथ मिलाओ। अब श्री देवी जाने के लिए तुम तैयार हो जाओ। ये लो तुम्हारी गाड़ी आ गई है, ये लो बैठो गाड़ी में। लो साहब, लौंडिया तैयार हो गई है जाने के लिए। अब देखो 3 आइटम और रह गए जिसके। पहला आइटम देखो ये है, इस फंदे के बीच में वो निकलेगा। ये वो आइटम है जी जो कभी हनुमान बजरंग बली ने लंका में आग लगा के 32 फुट की छाल लगाई थी, समंदर में कूदा था, उसकी नकल है। और दूसरा आइटम है जी, देखो गाड़ी चलेगी तीसरे का। और तीसरा आइटम पता बाल को कौन सा होगा? इसकी और मेरी लड़ाई होगी। सब बच्चे बोलो लड़ाई देखोगे, जोर से बोलो लड़ाई यार। अभी नहीं यार, अभी नहीं, बात तो सुन ले, बात तो सुन ले यार, बात तो सुन ले यार, बात तो सुन ले। लड़ाई देखो पूरी होनी चाहिए 11। अबे ओ बात सुन, बात सुन। पहले तुम फंदे के बीच में को निकल के दिखलाओ। ये क्या बात हो गई? तुम्हारे सिर में दर्द हो गया तो देर किस बात की, निकल के दिखलाओ। सही बात है। कहता पहला खेले, इतनी देर नाचा, हाय तौबा करी, पापी पेट कर। पेट का फिक्र मत कर, तेरा इनाम के नाम फल से मिलेगा यहाँ की। और इधर गुरुजी बैठे हैं, ये तुम्हारा इनाम के नाम जरूर देंगे। तू अपना आइटम पूरा कर, उसके बाद तेरा इनाम सबसे मिलेगा। ये लो पहलवान साहब, ये तुम्हारे खेल के नाम का इनाम है, लो पकड़ो। दुआ करो इनके हक में, सच्चे दिल से दुआ करो। ये बात। चलो तुम फंदे के बीच में को निकल के दिखलाइए इतने ऊपर को। अरे तेरा इनाम सबसे मिलेगा, पहले तुम निकल के दिखलाओ। चलो जल्दी से, देर मत करो। फंदे के बीच में को कैसे निकलते हैं? ऐसे।
Everyone who's done
एक बार और निकल के दिखलाओ जल्दी से।
this process is the density of state. You need your postcard, podcast,
एक बार और निकलिए,
and to get information
जल्दी से निकलिए, जल्दी से।
you need your wave card, chart card, energy.
एक बार और
This is my model low.
ये लो साहब, जल्दी से निकलो। अब आप लोग गाड़ी चला के दिखाओ, गाड़ी तुम्हारी कैसे चलती है। गाड़ी दमादम चलाया करो। गाड़ी चली, कितने राजी, कितने खुशी, सबसे नमस्ते करो, हाथ मिलाओ, सबके हक में दुआ करो, मालिक के सामने मत्था टेक। चलो साहब, खेल समाप्त हो गया। गुरुजी अब अपनी वीडियो
इस पर गाड़ी बैठा के चलवा दे।
नहीं है ना, बैठ।
अच्छा बैठा दो, बैठ जा।
चल भाई, गाड़ी खा भाई, गाड़ी खा जल्दी से।
बैठे
बैठे तू फ्री दे।
ताली बजा दे एक बार,
ताली बजाओ, बजाओ भाई, जोर से बजाओ भाई, जोर से बजाओ। दो एक बार। रोशन ऑडियो वीडियो चैनल देखने के लिए आप सबका धन्यवाद। बोलो, चैनल को सब्सक्राइब जरूर करना।
Absorption Spectra. I think it looks fine. What do you guys think?
Yeah, yeah, man. ये मादा, ये बहुत बड़ा। आपने कैसे ऐसा उनका काम नहीं हुआ है। अगर भैया तीन साल पहले गाँव पर लगा दिया था, तो दूसरा ख्याल था जो दिखाओ हम अपनी का लाके दिएगा, चीज नहीं है। लगाया उनके नशे के सुने सुने और हमारे
Yeah, you just kind of have to turn it off because the bond extends. If you don't fix that, it will just kind of go in different space.
So it's fine?
It's fine, yeah.
So it's showing it across the border of boundary conditions.
Yeah. So that's why you get those weird kind of, they're artifacts. They're not real. They're not like, so your stuff is looking pretty good.
Thank you.
Actual questions? Questions 1? Questions 2? Question 3? Okay, let's thank anyone. Last but not least, Sudipta Saha, and we are just 10 minutes behind the schedule, which is a record. So he will be first among a very long line of presenters who speak not about polymers.
Hi everyone, this is Shaha. I'm going to talk about the properties of aluminum doped solid state electrolyte. So before starting my presentation, I will just try to make you guys introduce what I am going to talk about today. So we will talk a little bit about the structure on which I am working on, and then the calculation steps that I have followed for these things, and then the results that I have found, and I will try to describe why this is happening. I will try my best. I'm not sure how much I will go through this thing, and then hopefully we will conclude at a certain point. So this LLGO material that basically results from lithium, lanthanum, zirconium oxide. This is a solid state electrolyte, and solid state electrolytes are getting attraction in lithium ion batteries sector because of its high chemical, electrical and mechanical stability. And among different solid state electrolytes, LLGO material has been highly used recently, and many people are working on this material because of its high conductivity. So in this LLGO material, this garnet type, that's basically a garnet type structure, and it has two different phases, the cubic phase and the tetragonal phase. These two different phases, cubic and tetragonal, almost everything is same, but the main difference is about the occupancy. In tetragonal site, out of tetragonal phase, out of 56 sites, all 56 sites for lithiums are fully occupied by 56 lithium atoms. But in case of cubic, these 56 sites are partially occupied by 120 lithium atoms. So there are atoms in 24D site and there are atoms in 96H site. So 120 lithium atoms partially share the 56 sites. So that's the main difference between the cubic site and the tetragonal one. And I have worked on the cubic one because cubic one has been reported as high bulk conductivity compared to the tetragonal one. So in this cubic LLGO material, okay, so that is the structure of the cubic LLGO material before doping. So in this structure, I have just showed these balls. These balls are basically partial, like here, 2 lithium atoms are partially sharing these places. So there are two different sites, 24D and 96H, having two different partial occupancy. Like for 24D, the partial occupancy is around 0.934, and for 96H, the occupancy is around 0.312 or something like that. So these green balls basically represent the partially occupied lithium sites. So there are 56 different sites, and we have 120 lithium atoms. And this one is basically the aluminum dope structure. So what I have done here, so I have removed 3 lithium atoms from the structure, and from 3 different lithium sites, and then in one site I have put 1 aluminum. So basically we have, so that the structure remains charge neutral. So in the structure now, in my structure, what we have, earlier we had 56 lithium atoms, now we have 53 lithium atoms, and now we have 1 additional aluminum. So the structure is charge neutral and aluminum dope. So I will try to compare whatever I am finding for this aluminum dope structure and undoped structure. So for doing these calculations, if we divide my whole calculations in different parts, so it can be in general in 3 different parts. In first part, I have worked on the Python, so that I have modified the structure so that I have removed the partial occupancy, and I have considered that yes, in this cubic structure I have actually 56 lithium atoms in 56 different sites with occupancy 1. That means I have to remove 120 minus 56 atoms from the structure. So how will I remove that? I have randomly generated around 10,000 structures, of which in each of the structures we have 56, not 120 lithium atoms. And then I have calculated the, so if we go through this slide, yeah. So then I have calculated the UR energy for each of the structures. So, and sorted them. So out of 10,000, I have taken 5 or 10 structures having the minimum UR energy, and then done the geometrical optimization in Bsb so that I can get the minimum ground state energy for that stable cubic structure. And after that, I have done the doping. And so in case of doping, so I want to place 1 aluminium in 56 sites. So at which site should I place my aluminium? That's a big question. So I have placed the aluminium in each of the 56 sites, and I have done the same UL energy calculation for 56 structures, and then sorting, and then geometrical optimization, so that I can get the structure having minimum UL energy and minimum ground state energy. So that's so far I have done in Python. And after Python, the next part is the main thing, the Bsb simulation. So in Bsb simulation, the things are pretty simple. I have done the geometrical optimization first, and then I heated the structure, and then I have done the molecular dynamics. And after that, up to the molecular dynamics, I have calculated the density of state and absorption spectrum, and I had it planned to see the change in the activation energy and diffusivity or diffusion coefficient. That's why I have done the trajectory analysis in a third-party software in molding, and then so that's all basically I have done for the simulation purpose. So those are 2 structures for undoped lithium LLGO, and this one is aluminum doped. So in this undoped lithium structure, that one is geometrical, both of them are basically geometrically optimized. And here, so these reds basically represent the oxygen, the dark greens are lanthanum, the light greens are lithium, and in this structure I have just kept only lithium and aluminum for better understanding. So these are 2 videos, maybe it can help you to see. So these are the videos for geometrical optimization. So that means when the temperature is at 0 Kelvin. So after that, so these are the density of state and absorption spectrum for geometrically optimized undoped and 1 aluminium doped structure. So if we see the undoped and 1 aluminium doped structures density of state, we can see that in aluminium doped structures we have some defect orbitals in the band gaps, and I am thinking that these defect orbitals has been created due to the aluminium doping, and the band gap has reduced a little bit from around its 0.2 to 0.5. So the band, 0.4 around. So the band gap has reduced a little bit, but still the band gap is beyond 3.5 or 3.4 electric volts. So it's still a ceramic material. And in case of absorption spectrum, if we see, we can see here actually, we can see in the paper that the absorption spectrum for undoped and 1 aluminium doped structures are almost same features, except in 1 aluminium doped structure we can see some unique features here, here, and here. Those are not present in undoped structure. So I believe that those have been created due to the aluminium doping. And then, So these are the density of states of undoped lithium lanthanum zirconium oxide after molecular dynamics. So nothing has changed actually. So whatever we have found for undoped structures, these three graphs are for three different temperatures. This one is for 1000, this one is for 1600 Kelvin, and this one is for 2200 Kelvin. So everything so far same as expected, and here in case of 1600 I can see few defect orbitals which is not present too much in the 2200 Kelvin's density of state graph, and the band gap has reduced a little bit, around 0.2 to 0.5 after the heating and molecular dynamics, but yeah, everything seems normal and expected. And in case of density of state for one aluminum doped LLGO structure, we can see that in 1000 Kelvin structure there is no unexpected orbitals in the band gap, but in case of 1600 we can see few, and in 2200 we can see few more defect orbitals. So basically what we can say from here, that with the increase of temperature, more and more defect orbitals are seen in the band gaps, and this may happen because of the surface electron of the structure. I'm not 100% sure, but it's my understanding that this may happen because of the surface electron of the structure. So, and this one is the video for the molecular dynamics of the at 1600 Kelvin. So, and this one is for 2200 Kelvin. Yep. So the same thing again actually. So that is the third part of the whole calculation or whole plan. So in this part I have calculated the diffusion coefficient and the activation energy. So how I have done that? I have basically followed this simple equation. So how did that? After the molecular dynamics, I have plotted the mean square displacement versus time step graph, which basically gives me the slope, this thing, mean square displacement divided by delta T. And with this equation, I have calculated the diffusivity at each of the temperatures. Like I have arranged the temperature from 1000 to 2500, and for each temperature, I have calculated the diffusivity, and then I plotted the logarithm of diffusivity against 1000 divided by T. And then what I have found that at temperatures from 1000 to around 1400, the diffusion coefficient for aluminum doped structure is higher than undoped structure, and gradually it decreases. And another more interesting thing that we can find from here, that the slope of the aluminum doped structure is higher than the lower than the slope of the undoped LLGO structure. So why this is important? So to understand that, maybe we can go to this slide. Yeah. So why this is important? Because from that curve, we can easily, using this equation, we can easily calculate the activation energy. And what we calculated, the activation energy for the aluminum doped structure is lower than the activation energy for the undoped structure. That's expected actually. But both the values are lower than the experimental values. There are a few reasons, like we have considered so many standard structure, like not experimentally, and we have calculated the diffusivity at very high temperatures and then extrapolated it. That's not normal. In our experimental cases, those are run at very room temperatures. So that is the reason why our experimental value is activation energy is lower than that. And as the activation energy of aluminum doped structure is lower than the activation energy for undoped structure, and diffusivity is higher, so it basically represents that the conductivity for the aluminum doped structure will be higher than the conductivity for the undoped structure because conductivity is directly related to the diffusion coefficient or diffusion. So that's all I have done so far for this project, and thank you.
Okay, thanks. Any questions about ionic conductivity?
So you have really nice conclusion. Looks like you really have clear results with this. But did you try to compare with experimental data on the systems? Is it consistent or at least comparable?
Yeah, I have considered that, and I have also compared my result with another result. So maybe I can share a paper with you or a presentation. I have just prepared it today.
No, but
the things are pretty normal. But the only difference is that in case of experimental, the conductivity usually 10 to the -4 range. In my case, it's around 10 to the -3 or 10 to the -2.
10 to -3. So you have one order magnitude.
Yes, and the reason is that we have actually this is a pretty ideal structure. It's not room temperature condition, it's very high condition. At high temperature condition where the structure may disorder and the conductivity may be higher. But in case of room temperature it's not.
More questions about ionic conductivity? If no, let's thanks for the concluding remarks. Many thanks to all visitors for coming in and providing supportive and inspiring discussion. Many thanks for all participants of the course. There will be collection of feedback, and after you will learn about your grades very soon. And special thanks to National Science Foundation 108. They know that
I see it's
zero Department of Energy and their nurse facility, DTU CCAST facility, and Professor Kirina and her group members, Levi Weistrom and Javed, who provided access to Photon server, which was very helpful for the course. And also there is a hope that all participants of the class will be able to utilize their skills to facilitate their research in the continuation of their research life. Let's thank we are on recording, and there was a photo at the beginning. Okay.
Oh, I missed it.
You missed it.
Oh.
I also missed it.
We will screenshot and.
Well, take another photo right now.
Yeah, let's.
Let's take everyone and participate. Not everyone.
So.
Visitors as well.
Okay.
Just line up here and make another photo.
I think we have another.
Yes.
Oh, there's a will, there's a way.
There's no will here.
Yeah, you're grad students, so that's
Everyone.
He said everyone.
Yeah, you don't get all of this.
Let's go.
Come on, guys. Come on. Run.
Why are you wearing special?
You should be there because half of the class was from your group.
Oh.
Come on, you don't need to.
You need to stand in front. You're
just in this. Otherwise, it will be not.
Short people in the front. Tall people in the back.
Oh, I should have.
Are we organizing this in any particular way, or just like
viability of research?
I
don't want to hurt the board.
You guys can push this.
Where is this? Oh, yep.
That's a picture.
I'm not tough. Yep. Yep. Looks good.
Svetlana.
Thank you.
Should we swap?
She wants to.
I'm okay. Okay, yeah. Thanks everyone, and meeting is dismissed.
Awesome.
Thank you. All right, one more class.
One more class.
Where do you want the feedback?
Oh, I'll collect it. Just put it on my desk.
Oh, you got it.
Oh God.
I'm actually going to buy lots of module files. So it happened around the time. Remember the ISMR that we had this past summer back in the drivers? For 2 days I well, when I found out that
No, I'm gonna dig it.
Yes.